Good day, everyone. Welcome to our presentation on the research side outlet cyclone separator performance on powder material separation. This is a CFD and experimental study. I am Joeffrey Duran, a faculty and professor here in St. Louis University, Baguio City, Philippines. The content of our presentation will be on the introduction, area of interest, innovation, methodology, results in discussion, and finally, conclusions and recommendations. So for the information of everyone, the cycle separator is a device that moves particles from a gas stream using centrifugal action. So these types of device have posed an alternative device for industrial aerosol sampling and air pollution control device, which works within the range of 2.5 to 10 microns for the particulate matter. So why have we studied this particular design? So way back in my master's studies, as well as guiding students in their undergrad research studies, so we have developed this particular design wherein the outlet is on the side. Well, the typical cycle separators have their outlets on the top. So further analysis have involved experimentation and statistical tool in our previous studies. However, we have not yet done much on the simulation study. So these are just some of the innovations and modifications that have been done by the other researchers such as Kalsayed and Lakor, Zhang, Venkatesh, and others. This is just a presentation. This is just a presentation of our previous published study. However, this particular study is not yet optimized, and this is using a a particular simulation software using which is ANSYS. So what were the methodology that we have done in our research? So firstly, we have undergone the usual modeling using our 3D CAD. We have this initial design from our previous study. Then we further optimize this one. Okay, this is the past initial design dimensions, and we have came up with this particular design. So if you could notice, we have separated the inlet and outlet ports. We have separated the distance, and it has a longer cone length. So furthermore, the mesh or the discretization in our study is using, or we have used tetrahedral phase mesh to accommodate the um, irregular connections within the boundary of our cyclone separator. So if you could notice, there are no regular square or rectangular shapes in our design due to the irregular shapes in our cyclone separator volume. So for the turbulence model, we have opted to make use of Reynolds stress model for the reason that Reynolds stress model actually has a more robust design and usage. So RSM is more preferable than other models due to its 7 transport equations as presented here below. Okay, and it also um, predicts more realistically the swirling flows within the set boundaries. To get the separation efficiency in the simulation, we have made use of what we call discrete phase methodology. So the particle injection was done using the DPM, an approach used to define the path and separation performance as studied by Azadi et al. Here are the equations for our DPM. So this was used to define how much the cyclone separator was able to remove the particulates. As part of our performance indicators, we have made use of the pressure drop, which is a measure of energy consumption and how well the gas stream will be able to move through our cyclone separator. The second one will be the removal efficiency or the separation efficiency of how well the device takes out the particulate matter within our system. So just for a comparison, we have also included the past experimental data from our previous or from the previous iteration of this study. And we also have included the numerical simulation of that particular past experimental data. In our work, we have included the schematic diagram of our experiment. So here we have the particle feeder. It will be, it was injected to our system using a makeshift hopper. Then it was introduced into our system, wherein the velocity was taken as well as the pressure using a manometer in replacement for the pressure gauge. Now, on the bottom part of our cyclone, we have collected the dust to be measured in the latter part of our research. As well as for this one, we also have collected the remaining particulate matter at the end part of our process. Now, this compressor or pump setup here, we have made use of a vacuum due to the unavailability of other components. In actual design or in actual measurement, we have this um, infographics, as you can see. So we have the inlet here, then we have the vacuum system on the end part, and the pressure is measured by a manometer. And for the inlet velocity, we have made use of an anemometer. Also, at the bottom part, we have placed a collection bin. Unfortunately, it was not pictured here. So pardon me for that. No? Now, for the results in discussion, based on past simulation results, the pressure drop is around 80.8412. So take note, this is for the simulation results. The separation efficiency is taken at 45.48. Based on the past experimental results, based on our um, past data, the pressure drop is around 288.34 pascals, and the separation efficiency is somewhere around 60.34. If you could notice, there's a mismatch of the data, so that's what we have worked around. Based on the current simulation results, the pressure drop reduced significantly. So the pressure drop based on the simulation is 3.82 pascals, whereas the separation efficiency is measured at 83.59%. Based on the current experimental results, the pressure drop is reduced to 33.35 pascals, and the separation efficiency is given at or is measured at 81.82%. So just for for a comparison, the velocity and pressure profile of our device. So we have here on the left side, we have as you can see, the inlet is um, reddish to orange color to signify that it has a high inlet velocity. So as it traverses through our cyclone separator, if you can notice, there is a loss of energy or loss of velocity, I should say, on the lower part. So if you could notice, some of the particles, due to the low velocity, some of it will be falling down, and some of it will be moving through this outlet. In part of or in line with the discussion of velocity, we also have our pressure. So if you could notice, a moderate pressure is generated here. It's not yet the highest because the highest is the one directly hitting the wall. So if you can notice, there's a red patch of pressure here on the inlet wall, or rather the wall of the cyclone. Now, as we go along with or as it traverses through our cyclone separator, the lower part is of low pressure as well as the um, outlet part on this upper portion. So in this case, the difference in pressure actually creates the flow in our system. So we have high to low pressure in our cyclone separator. Now, just to add, we also have our particle trajectory profile. So if you could notice, it will enter here, and most parts are falling down through our lower conical section. And some parts are moving through our outlet section here on the upper section. Now, for the experimental results, we have done 10 trials, and the average of each trial is given here. So we have the inlet pressure, outlet pressure, up until our separation efficiency. Now, if we're going to average that one, we will be getting the measured 83 point, the 81.82 um, percent separation efficiency in our study. Now, there's a close resemblance of the simulation efficiency, which is at 83.59 based on our CFD study. Now, if you're going to take a look, we have also included the first version of the side outlets cyclone separator, which is at 45.48 and 60.34% for the separation efficiency, respectively. Now, we have solved we have validated our results using the separation efficiency. However, we still need to work around um, with the tenfold difference of the pressure drop. Nevertheless, we were able to define and to validate our results in the separation efficiency section. Now, to conclude our analysis or our study, the CFT analysis and experimental study were performed to validate the performance of a modified cyclone powder for powder material transport. In this study, a previously optimized side outlet cyclone was investigated using simulation approach, performing at 83.59%. So in the validation, the modified cyclone was fabricated and evaluated based on its cyclone efficiency, revealing 81.82 performance. The two methods have validated the collection capability of the cyclone separator for powder materials, with operations being considered at, as a cost-effective means, even at a low velocity of 2.52 meter per second. So while this study provides an alternative for powder separation and transport, it is still recommended that we further study the effect of varying inlet velocity to the performance of cyclone separators, as it is directly linked to the efficiency. Furthermore, there is also a need for us to have further study on the pressure drop since it is related to the power requirement to overcome the pressure buildup within the equipment. So for further questions and clarifications, I will be available at this email address. So thank you for listening and have a wonderful day.